This is a really exciting real-world example of putting AI to work for data scientists. As Jensen was saying, we're working with a network operator that has 25 million subscribers connecting to 500,000 LTE towers and Wi-Fi networks. Those connections they're really the lifeblood of this business, and that data is super important. So what we're going to show is how we can put AI to work to help the network operator make smarter decisions using these predictive algorithms.
Now, the decision, just to go to the end and work backwards,
Sure.
The decision they're trying to do is they're trying to figure out where to place Wi-Fi access points to offload from the cellular traffic so that they could provide the best possible quality of service, and then, of course, and to increase the capacity for their company. But you don't want to place it randomly everywhere.
They're adding 10,000 of these Wi-Fi access points per month. That is a big decision. They got to decide where to put them. And they can save a lot of time and money if they put them in the right place. And so what we're going to do is help them predict where to put those Wi-Fi access points.
Okay, that's awesome. And so the first step, of course, is we have to take the data in. We have to do basically ETL, extract, transform, and load. We have to do basically data analytics.
And this is a lot of data, Jensen. It's a terabyte of data per day that they've got coming in. Now, when you're talking about data scales that big...
Well, usually, you know what people do when they have a terabyte of data that comes in every single day? Ignore it.
That's right. That's right.
Yeah, that's right. Because tomorrow it's going to come back again.
That's right.
And you'll ignore that one too. Because it'll come back next week.
That's right.
That's the beautiful thing about recurring data. All right, but obviously they would like to use this data.
Yeah, this terabyte of data.
Their business.
Yeah, this terabyte of data is not also a really clean set of data. Of course, it's coming in from multiple different data sources. They've made some acquisitions over the years. That means they've got gold mines of data that they all need to combine into a single taxonomy.
Now, the industry calls it, give it a great name. It's called a data lake.
Yeah,
right?
well.
And the data lake's got all these different formats. It's all messy data. And some people call it dark data because you're never going to look at it again.
Yeah, to your point, what they were doing before was spending 8 days to be able to transform that data into a usable set of data. And this was all done manually. We had data scientists, dozens of data scientists, spending their time transforming this data to make it usable.
So let me see if I understand. You got a terabyte of data coming in every day. It takes you 8 days to process 1 terabyte of data.
Yeah, to make it usable.
Uh-huh.
So guess what?
Pretty soon, you're going to be infinitely behind.
Yeah, guess how many days of data we're not getting watched, right? So here's what we've got. On the left-hand side here, you can see this sort of incoming data. This is the complexity of the data that they had coming into the system. Dozens of different sources, all kinds of different formats. We're going to use a product called Datalogue, a really awesome product for being able to transform that data into usable data. The first step in that process is...
By the way, Datalogue is really fantastic. So this is Tim's company. I think Tim is watching. Tim, good job. Go ahead, Aaron.
Yeah, they are great. So what we're going to do first is define an ontology. This is basically just a knowledge graph that helps us transform what the data is that we have to the data is that we want. And so we've defined here the different data sets that we want. Each of these data sets, then, we can use AI to be able to transform the data we have into this data set that we want.
Yeah, and now what's really amazing, what Aaron just said is this. Just imagine. So you have basically data, let's say you have data sets coming from 10 different places. It's the same data. It's about the same thing, but the format's all different. The names that they use, the labels that they use, the columns they use, the features, the names they use for the features are different, but just a little different. Just a little different. You know, maybe your name's spelled just a little differently. If you and I were to look at the database, we would be able to tell that this column and this row is the same thing. But to a computer program, they're basically exactly different. Now, what we need to do is we need to have these AIs that are basically looking at all of this data as we're taking it in and realize that, you know what? That JEN-SEN and JEN-HSUN is the same person. It's the same person. It's okay.
Yeah.
Put them all in there.
Let's go look at actually what it looks like when we train these models. So this is an example of a model that we've trained for being able to predict these values. You can see that the different values that were coming in on the left-hand side, the values that we were predicting on the top there. You can see how successful this model is at being able to determine the different kinds of data coming in with the different data that we need in our ontology.
You were off by 2.
Yeah, well, so this is interesting though, right? Because sometimes you'll confuse an IP address for a different kind of data. Sometimes these things they look the same sometimes. The good news is we've trained this model so well that it's 99.9% accurate, which is much better than investing the 8 days worth of data scientist time to be able to produce those same results.
No, it would take days to do this by hand.
That's right. We want to automate it.
Days to do this by hand, right?
Yeah.
Not to mention just the computation of loading it and reformatting and then joining it and grouping by this and doing the SQL processing that you guys are familiar with, doing the SQL processing on it. It takes so much energy to do it. Eventually, you have this thing called a data frame. That data frame then comes into another amazing product. This amazing product is from a company called Omnisci, isn't it right?
I've heard of that company.
Yeah.
This is a company called Omnisci.
That you and Todd started, and Todd, is Todd out in the audience?
Todd's right here.
Todd, good job, man. Good job. So Todd realized the importance of GPU-accelerated data science, quite frankly, almost before everybody, practically, not just momentarily before me. Okay? And then he came and told me, then I realized, hold on a second, this is a high-performance computing problem. And so we've been working together for some time. Omnisci, you guys are doing amazing work. Now here's the data frame.
Yeah, so now we've got all this clean data, right? Now we want to actually put it to work. So we're going to bring it into Omnisci. Omnisci is a SQL database that is built to run on GPUs, and it also has a visualization engine. Let's cut to the dashboard so we can see what that looks like. Now, this is 500 million rows of that network access data that we were looking at before. This covers 215,000 access points.
You got to let that moment sink in. You guys know what a spreadsheet with 500 million rows look like? I know.
This is 200.
I've never seen one that big.
Yeah. 215,000 access points across the entire US. On the left-hand side there, you can see this really nice heat map showing where those access points are and where they're being used the most. Let's zoom into Ohio, actually, just because you can see how easy it is to zoom in and get a much clearer picture of a specific part of your data. So now, look how we've zoomed in, and now we're seeing the detail of what's happening in the state of Ohio. I'm going to go use the time chart here in the middle to zoom in not just by location, but now by time as well. See how when we changed to the chart at the bottom there, now we're seeing hourly results at the top. And as we scrub over to the right, we're seeing all of the charts changing in real time to show us what happens at different time frames in that data set. Now, Jensen, this is the cool part, because what's actually happening behind the scenes here, we're running hundreds of SQL queries against that database. There is no way you could do this on CPUs. It's only possible because we've architected to run on GPUs.
It was like yesterday morning that SQL was a batch job.
That's right.
You guys are now watching this in real time.
And
this is craziness.
This is no indexing, no aggregation. This is 500 million rows of raw data.
Are you guys getting this? SQL used to be something you would run with Hadoop, and it would be a batch job.
That's right. That's right.
You know, now you're doing this interactively, and you're visualizing it in real time. It's incredible.
Now, this is just the first step, though, Jensen, because now we're actually seeing the historical data. Let's get to the predictions. Let's get in our time machine and start to see what's happening in the future. We're going to do that using a Jupyter Notebook. So we'll switch over to the Jupyter Notebook now. And this is an interface that all data scientists are familiar with. It's Python. We're going to actually, in the first step there on the left, we're going to actually get a pointer to that data sitting in the Omnisci memory, in GPU memory. We're going to use that pointer to do the feature engineering that you talked about before. And on the right-hand side, we're going to run our XGBoost to do the training, to do our machine learning. Very familiar toolkit here of tools. That pointer is exactly a pandas interface, which is what you're looking for if you're a data scientist, right? So these tools give us those predictions. Once we get those predictions, we're going to push them back into Omnisci so that we can make a complete visualization of what that looks like.
Did you guys just see this? So first step is data analytics. And within data analytics, you could use Omnisci to visualize it. Just take a look at the data so you can get a feeling for it. Then once you do that, you've done the feature engineering, you take that into that data frame, you put that into XGBoost. That XGBoost is your machine learning algorithm. That machine learning algorithm is going to take the previously collected information and all of the features, and it's going to learn a model that predicts the future from those features. Okay, predict the future from those features, and it's going to come up with a new model.
And let's not forget about Rapids. Rapids is an important piece of all this that ties it all together, right? So we're using that here with these data frames that you talked about to be able to do this kind of prediction. Okay, we pushed the data back into Omnisci. Let's go back to that dashboard now so we can see what that looks like. You'll see on the time chart now, we have this dotted line that goes into the future. So as we scrub through, again, we see that same interactive experience of scrubbing through the data, and now we're seeing predicted results for where we think the usage is going to be across the state of Ohio. And you can see the same sort of interface, the same interactivity that you get now using these predicted results coming from Rapids using cuDF.
And guys, you just saw in just a really quick moment here, predictive analytics in practice, from the beginning to the end. And if we could accelerate everything, and what Aaron was saying was, it's called Rapids. Rapids is the machine learning framework, the data analytics, the data science framework that we open sourced. Underneath it is a whole bunch of engines. Those engines are basically CUDA-X. And Rapids is now open sourced. And the important thing is you see down here, this is where I grew up, Oneida, Kentucky. And there's no traffic there at all. I think, here, somebody type in Oneida, Kentucky. Let me just, Oneida, Kentucky. Let's see. Just one access point. Come on. Give us one access point. That's it. That's where I grew up. One intersection. I'm not kidding. Not kidding. All right, so everybody's still baffled. They're going, that can't be right. That can't be right. That is right. So that's where I came to, United States. And so here we saw the entire platform. How long did it take before, and how long does it take now?
Right, so we were talking about 8 days before, just to get to a point where we had some data we could do something interesting with, and then it was taking us hours to do queries after that, right? Now we're talking about 4 minutes to be able to get data the way we want it. That's near real time. And then what you're seeing here is absolutely interactive engagement with that data. So it's just a completely different paradigm of what's possible with this data.
So here we go. Data scientists, the most sought after professional in the world today. They're sought after in every single industry, in every single company. And then once they get them, they make them sit 8 days as they work on data that is 8 days old, 7 days old. Okay? And so that makes no sense. What we want to do is we want to accelerate their work, give them the instrument of their science, give them the instrument, the tool of their science, so that they could do their life's work, and to do their life's work as quickly as possible. Ladies and gentlemen, Aaron Williams.
Thanks, Jensen.